Module 7, Evaluating Measurement Uncertainty. Slide 2, Overview. In this module, we'll talk about how to evaluate and propagate measurement uncertainty. We'll illustrate the techniques with several examples along the way. After that, we'll consider some of the pitfalls that might cause you problems, and at the end, we'll mention some of the tools that are available to make it all easier. Slide 3, Mathematical Model. Typically, one doesn't observe the final result of a measurement directly from an instrument. Instead, the result is calculated from the values of other observed quantities using a mathematical model of the measurement. The model might also be called a measurement equation. This model relates the values of the directly measured quantities, the input quantities, to the final result, which is called the output quantity, and which is also the measurand. Slide 4, Measurement Equation. The mathematical model of a measurement might consist of a single equation or a set of equations. For the purposes of this training, we'll do what the GUM does and present it abstractly as one equation, y equals f of x1 through xn. Here the symbol y denotes the output quantity, and x1 through xn are the input quantities. The function f is called a measurement function. When the GUM presents an abstract measurement equation like this, it uses uppercase symbols for the input quantities and the output quantity, and that's what we're going to do. Slide 5, Input Estimates. Making a measurement requires that you estimate the values of the input quantities somehow, and then plug them into the measurement function to calculate the value of the output quantity. The estimated values of the input quantities are called input estimates. And these will be denoted here abstractly using lowercase symbols, x1 through xn. So uppercase x's and y's denote the abstract quantities or variables, and lowercase x's and y's denote the estimated values of those quantities. Slide 6, Output Estimate. Using the model and the input estimates, one calculates the value of the output quantity. The calculated value, denoted here by a lowercase y, is called the output estimate. The equation at the bottom of this slide is the same as the original measurement equation, except for the fact that all the symbols here are lowercase, indicating that we're plugging in actual values for the input quantities and for the output quantity. Slide 7, Evaluating Uncertainty. We've calculated the output estimate, y. Now we want its combined standard uncertainty. First, we need the standard uncertainty of each input estimate, x sub I. Then we'll determine how much uncertainty each of these contributes to the total uncertainty of y. There are many ways to do that first step. We'll consider some of them next. Slide 8, Methods of Uncertainty Evaluation. The GUM describes two general categories of direct uncertainty evaluations for input estimates. It calls them Type A and Type B. A Type A evaluation is an evaluation of uncertainty by the statistical analysis of one or more series of observations. A Type B evaluation is any other kind of uncertainty evaluation. Slide 9, Type A evaluations. The canonical example of a Type A evaluation involves making a series of replicate measurements of an input quantity x sub I. You estimate the value of x sub I by the average of all the results, and you estimate the standard uncertainty by the experimental standard deviation of the mean, often called the standard error of the mean, but usually not by metrologists. Least squares regression is also a Type A method. Anytime you have a well-defined number of degrees of freedom, it's probably a Type A method. Slide 10, Example, Type A evaluation. Suppose you make 6 measurements of an input quantity. In this example, the 6 measured results are 12, 9, 12, 10, 11, and 9. The input estimate is the average of those 6 results, which equals the sum, 63, divided by the number of measurements, 6. That equals 10.5. The experimental standard deviation of the 6 values is 1.378, and that's shown on the next slide. The standard uncertainty of the input estimate is the experimental standard deviation of the mean, which equals 1.378 divided by the square root of 6. That equals 0.5627. Slide 11, Example, Type A evaluation. On this slide, the calculations are written out in detail. First is the calculation of the average, the sum of the 6 values divided by 6. That's 63 divided by 6, or 10.5. Next is the calculation of the standard deviation of the individual values. Add up the squares of the deviations of all 6 values from the average, divide by 6 minus 1, and take the square root. The result is 1.378. And finally, divide that standard deviation by the square root of the number of values to get 0.5627, which is the standard uncertainty of the average. Slide 12, Type B evaluations. By definition, any direct evaluation of uncertainty that isn't type A is type B. There are many examples of type B evaluations. One example is Poisson counting uncertainty. It's pronounced Poisson in French, but I'm going to Americanize it and say Poisson. Another is uncertainty obtained from a tolerance, for example, the tolerance for the capacity of a piece of volumetric glassware. And another is a value with uncertainty imported from an outside source, such as the activity of a purchased calibration standard. Sometimes a type B evaluation is based on professional judgment. That's accepted, so you shouldn't be afraid to make an educated guess. It's often better to guess than to ignore the uncertainty completely. Slide 13, first example, Poisson counting. In a typical radiation counting measurement, the standard uncertainty of the total number of counts, n, is estimated by the square root of n. The basis for that estimate is the fact that n usually has a distribution that is approximately Poisson, and if n has a Poisson distribution, the standard deviation of n equals the square root of the mean. The observed value is an estimate of the mean, and its square root is an estimate of the standard deviation. It's important to remember that this is a peculiar property of the Poisson family of distributions. You can't just take the square root of any measured value and call that its uncertainty. Slide 14, example, Poisson counting. Suppose we make a radiation counting measurement where the distribution of the counts is assumed to be Poisson. Suppose we observe 169 counts. The standard uncertainty of that value is the square root, which equals 13. Slide 15, low-level Poisson counting. You may sometimes see results reported as 0 plus or minus 0. That happens when the blank or background count and the sample count are both 0 and the lab estimates counting uncertainty by the square root of the counts. But reporting 0 plus or minus 0 or anything plus or minus 0 is a bad idea. The uncertainty of a measurement is never 0. For this reason, Marlatt recommends that whenever very low numbers of counts are possible, labs should evaluate the uncertainty of the count n by the square root of n plus 1. Slide 16. Example, low-level Poisson counting. Suppose the number of sample counts, n sub s, happens to be 1. Obviously, very low counts are possible, and this is a situation where the lab should add 1 to n sub s before taking the square root. The standard uncertainty is the square root of ns plus 1, which is the square root of 2, which equals 1.414. Slide 17. Second example, rounding. Suppose an input estimate is rounded to 0.8. Rounding a value loses information and therefore increases its uncertainty. The original unrounded value could have been anything between 0.75 and 0.85. How does one account for this uncertainty? It's actually pretty easy. You assume a rectangular distribution for the value centered on 0.8, which is the value after rounding, and with a half-width of 0.05, which is the size of the maximum rounding error. The standard uncertainty is the standard deviation of that distribution, which equals the half-width divided by the square root of 3. Slide 18, rectangular distribution. Here's an illustration of a rectangular distribution. It's centered on the input estimate x sub I, and its half-width, denoted by a, is the magnitude of the maximum possible rounding error. All values between x sub I minus a and x sub I plus a are equally likely. The standard uncertainty equals a divided by the square root of 3, which is shown here. Slide 19, third example, capacity of a pipette. There is uncertainty in the capacity of a volumetric pipette. It's typically small, but it's not 0. An ASTM Class A volumetric pipette has a stated tolerance A for the nominal capacity V. Any value in the range V plus or minus A is possible, but we'll assume that values near the nominal capacity are more likely. In this situation, we estimate the standard uncertainty using a triangular distribution, not a rectangular distribution. It's centered on the nominal value V, and it has half-width A. To get the standard uncertainty for a triangular distribution, you divide the half-width by the square root of 6, not by the square root of 3 as we did for a rectangular distribution. Slide 20, triangular distribution. Here we have an illustration of a triangular distribution centered on an input estimate x sub I and with half-width A. Note the values near the center are more likely than those near the endpoints. The standard uncertainty equals A divided by the square root of 6, which is shown here. Slide 21, example, triangular. Suppose the nominal capacity of an ASTM Class A volumetric pipette is 1 milliliter with a tolerance of A equals 0.006 milliliters. Assume a triangular distribution for the error and calculate the combined standard uncertainty of the capacity, V. The standard uncertainty of V equals the tolerance A divided by the square root of 6, which is 0.006 milliliters divided by 2.4495, or 0.00245 milliliters. Slide 22. Note: the uncertainty of the pipette's capacity is not the total uncertainty of the volume delivered. The total uncertainty depends on the operator's skill, among other things, but the uncertainty still tends to be relatively small when compared to all the other uncertainties in a typical radiochemical measurement. Slide 23. Rectangular and triangular, other uses. Rectangular and triangular distributions are often used when you can estimate a bound A for the largest possible error in the input estimate. If you know nothing else about the distribution, assume it's rectangular, in which case you divide the half-width by the square root of 3 to get the uncertainty. On the other hand, if you think values near your estimate are most likely, assume the distribution is triangular and divide the half-width by the square root of 6. Slide 24, fourth example, imported values. If you import a value that has been measured by someone else, such as a half-life reported by the Decay Data Evaluation Project or the National Nuclear Data Center, and you use the reported uncertainty, that's a Type B evaluation from your point of view. Or if you buy a standard with a stated value and a 95% confidence interval, you can perform a Type B uncertainty evaluation by dividing the half-width of the interval by the appropriate percentile of the standard normal distribution. Slide 25, example. Suppose the stated massic activity for a standard solution is 204.1 becquerels per gram with 95% confidence limits at plus or minus 3.2 becquerels per gram. What is the Type B standard uncertainty of that massic activity? Just divide 3.2 becquerels per gram by 1.960, which is the 97.5th percentile of the standard normal distribution. The standard uncertainty equals 1.6 becquerels per gram. Slide 26, uncertainty propagation. Typically, you calculate the final result of a measurement using a measurement equation, y equals f of x1 through xn. Then you measure or import estimates x1 through xn of the input quantities and calculate an estimate y for the output quantity by plugging the input estimates into the measurement equation. Slide 27, uncertainty propagation continued. One uses the same model to determine how the standard uncertainties of the input estimates combine mathematically to produce the combined standard uncertainty of the output estimate. The mathematical operation of combining the uncertainties of the input estimates to get the uncertainty of the output estimate is called propagation of uncertainty. Slide 28, how uncertainties combine. Suppose the standard uncertainty of x1 is 1.5 and the standard uncertainty of x2 is 2. What's the uncertainty of the sum x1 plus x2? The rule is that the uncertainties add in quadrature. That means you square each uncertainty, add those squares, and take the square root of the sum. The combined uncertainty in this case is not the simple sum of the two input uncertainties, 1.5 plus 2. Instead, it's the square root of the sum of the squares of the uncertainties. The squares are 2.25 and 4. The square root of their sum is the square root of 6.25, which equals 2.5. Slide 29, components of uncertainty. If the mathematical model is more complicated than a simple sum, think in terms of uncertainty components. An uncertainty component is the part of a total uncertainty of the output estimate, y, that is generated by just one input estimate, x sub I. Uncertainty propagation generally consists of calculating all the uncertainty components, squaring them, adding up the squares, and then taking the square root of the sum. Slide 30, sensitivity. The uncertainty component due to an input estimate xi depends not only on the uncertainty of xi, but also on how sensitive y is to changes in xi. If large errors in xi don't generate large errors in y, then y isn't very sensitive to xi. For example, there might be a large uncertainty in the time of sample collection, but the sensitivity of the decay correction factor to that time depends on the half-life. The sensitivity is much greater if the nuclide is iodine-131 with a half-life of 8 days than it would be if the nuclide were uranium-238 with a half-life of 4.5 billion years. Slide 31, components of uncertainty. The component of the combined standard uncertainty of y generated by the standard uncertainty of an input estimate x sub I can be denoted by u sub I of y. It's defined to be the product of the absolute value of the partial derivative of f with respect to x sub I times the standard uncertainty of x sub I. The partial derivative is called a sensitivity coefficient because it indicates how sensitive y is to changes in the value of x sub I. Slide 32, estimating uncertainty components. It is generally preferred that the sensitivity coefficients be calculated using the rules of calculus. But it's also okay to estimate the sensitivity coefficients or to estimate the uncertainty components without explicitly calculating sensitivity coefficients at all. An example is the Crogton spreadsheet method. One way to estimate an uncertainty component without calculus is given by the equation at the bottom of the slide. The equation shows that you calculate the output estimate twice, adding the uncertainty to x sub I in one case and subtracting it from x sub I in the other case. Calculate the absolute value of the difference between the two resulting values and multiply that absolute value by 1/2 to get an estimate of the uncertainty component due to x sub I. Slide 33, uncertainty propagation formula. The general equation for propagating uncertainty can now be written in two equivalent ways. In the first, we add the squares of the uncertainty components and take the square root. In the second, we effectively do the same thing, but each squared uncertainty component has been written as the product of the square of the sensitivity factor and the square of the standard uncertainty of the input estimate. The GUM calls this equation, in either form, the law of propagation of uncertainty. MARLAP prefers the name uncertainty propagation formula. It's not what we consider a law, it's really just an approximation formula. Slide 34, derivatives. The partial derivative of f with respect to x sub I indicates how much the output estimate y changes when x sub I changes by a very small amount. For example, if y equals 2x1 minus 4x2, then the partial of f with respect to x1 equals 2, and the partial of f with respect to x2 equals minus 4. For more complicated functions, you need either calculus or the estimation procedures mentioned earlier. Slide 35, example. Recall a very simple model from the previous slide, y equals 2x1 minus 4x2, and suppose the standard uncertainty of x1 is 1.5 and the standard uncertainty of x2 is 1. The component of the combined standard uncertainty due to x1 equals the absolute value of 2 times 1.5, which is 3. The component of combined standard uncertainty due to x2 equals the absolute value of minus 4 times 1, which is 4. Then the combined standard uncertainty is the square root of the sum of the squares of those two components, which equals the square root of 25, which is 5. The propagation of the uncertainties from the preceding example is illustrated here graphically. The equations on the left just summarize what we said on the previous slide. The illustration on the right is a right triangle. The lengths of the two legs, which are perpendicular to each other, represent the two uncertainty components, which are 3 and 4, and the length of the hypotenuse, the blue line, represents the combined standard uncertainty, which is 5. Just remember the Pythagorean theorem. Slide 37, small components. One consequence of the fact that uncertainties add in quadrature is that a small uncertainty component has even less impact on the total uncertainty than you might think. In the example shown here, the combined standard uncertainty, represented by the hypotenuse, colored blue, is almost identical to the larger of the two uncertainty components. Slide 38, correlated input estimates. The form of the uncertainty propagation formula presented earlier presumes that all the input estimates are determined independently of each other. If some of the input estimates are correlated with each other, you need a more complete version of the formula, which is shown here. It adds extra terms to account for the correlations. The expression U of xi and xj denotes the estimated measurement covariance of input estimates xi and xj. Each of these is multiplied by the product of the two sensitivity coefficients and added to the radicand. Each one is added twice since both U of xi xj and U of xj xi need to be included and they're equal to each other. Slide 39, what causes correlations? One reason that input estimates could be correlated is that they might be calculated from the same data. An example would be the parameters of a calibration line or curve determined by least squares. Physics is another possible reason. For example, the areas of two photopeaks in a gamma ray spectrum might be correlated. And another possible reason is the effect of environmental factors like temperature and humidity on measuring instruments, but these are usually too small for us to care about. Slide 40, correlations. The effect of correlations on the combined standard uncertainty might be either to increase it or to decrease it. Here we see a graphical illustration showing how a correlation might change the shape of the right triangle we saw earlier in a way that makes the combined standard uncertainty larger than it would be without the correlation. The geometric analogy still works, but the triangle is no longer a right triangle. Slide 41, Correlations Continued. Here we see an illustration showing how a correlation might make the combined standard uncertainty smaller. Either of these cases is possible. Slide 42, How to Estimate Correlations. One way to estimate a correlation is experimentally, a type A evaluation based on a series of paired measurements of two input quantities. The covariance of two output quantities calculated from the same data can be calculated using a formula similar to the uncertainty propagation formula. You might call this combined covariance. See MARLAP Chapter 19 for more details. Slide 43, Shortcuts. It helps to remember shortcut formulas for propagating the uncertainty of simple expressions like sums, differences, products, and quotients. For example, if all the input estimates x1 through xn are uncorrelated, and if y is a linear combination of those input estimates, where the coefficients c1 through cn are constants, the combined standard uncertainty of y is given by the equation shown here. Square each input uncertainty, u of xi, multiply it by the square of the coefficient ci, add them all up, and take the square root. Slide 44, Shortcuts Continued. Here's another example involving products and quotients. The output estimate y is the product of input estimates x1 through xk divided by the product of input estimates c1 through zl. Assuming all of these inputs are non-zero and uncorrelated, you can calculate the combined standard uncertainty of y by adding up the squares of the relative standard uncertainties of all the input estimates, multiplying that sum by the square of y and taking the square root. Slide 45, Shortcuts Continued. In radiochemistry, it's common to see a model of the form shown here, where y equals a net count rate, R net, divided by the product of several factors, such as efficiency, yield, and aliquot size. If there are no correlations, the combined standard uncertainty of y can be expressed as the square root of the sum of two terms. The first term equals the squared uncertainty of the net count rate divided by the squares of the denominator factors. The second term equals the square of y times the sum of the squares of the relative standard uncertainties of all the denominator factors. The same paradigm works when there are more factors in the denominator. Slide 46, Pitfalls of Uncertainty Evaluation. Pitfall number 1. Sometimes an input quantity appears in the mathematical model more than once. What's the problem? You might be tempted to treat each occurrence of the input quantity as if it were a distinct variable. It's not. Think about an extreme example. What is the uncertainty of x minus x? The same input x appears twice in this model. The uncertainty of the difference isn't found by squaring the uncertainty of x, adding the square to itself, and taking the square root. The uncertainty of the difference is exactly 0 because x minus x is always exactly 0 with no uncertainty. Slide 47, Example, Repeated Variables. Here's a less extreme, real-world example encountered several years ago. How to calculate the combined standard uncertainty of y, where y equals the quotient of x1 divided by the sum of x1 and x2. Does the uncertainty of x1 contribute more or less uncertainty to y because it appears in the model twice? If you say yes, then ask yourself, what is the uncertainty of z, where z equals x2 divided by the sum of x1 and x2? Note that z equals 1 minus y. Slide 48, Example Continued. The fact that z equals 1 minus y implies that y and z must have the same uncertainty. If you use calculus to calculate the sensitivity coefficients as shown here, you get the expression shown at the bottom, which is symmetric in x1 and x2. Neither x1 nor x2 contributes more or less uncertainty than the other just because of the number of times it appears in the expression for the measurement function. Slide 49, Pitfalls of Uncertainty Evaluation Continued. Pitfall number 1 continued. Sometimes variables that appear explicitly in the model are calculated from other variables that may or may not appear explicitly. That can tend to obscure the fact that some variables in effect appear twice. A good example of this occurs in AlphaSpec using a tracer, where the calculation of the tracer yield involves the counting efficiency. The efficiency has no effect on the final result, it simply cancels out. Slide 50, Pitfalls of Uncertainty Evaluation Continued. Pitfall number 2. Beware of some shortcut formulas when the output estimate is 0. Remember the radiochemistry example where y equals the net count rate divided by a product of factors in the denominator. Use the slightly more complicated formula shown here in the middle. Note the simpler formula shown at the bottom. If you use the simple formula, you'll divide by 0 whenever the net count rate is 0. These two are equivalent as long as R sub net is non-zero. Slide 51. Pitfalls of uncertainty evaluation continued. Pitfall number 3. Everyone likes to assume Poisson counting statistics so they can estimate counting uncertainty by the square root of the number of counts. What's wrong with that? Often nothing is wrong with that, but there are cases when counting combined emissions from more than one nuclide in a short live decay chain when the Poisson model isn't valid. In these cases, the square root of n usually underestimates the uncertainty. The departure from Poisson statistics is greater when the counting efficiency is high. Slide 52. Example. Radon-222 in a scintillation cell. The classic example of non-Poisson counting is counting radon-222 and its progeny in an alpha scintillation cell, also called a Lucas cell. You get alpha counts from radon-222, polonium-218, and polonium-214. The detection efficiency is usually high. The counts tend to occur in clusters as one atom decays through several states, not as independent events. The problem was described by H.F. Lucas in the early 1960s, but many are still unaware of it. Slide 53. Other examples of non-Poisson counting. You can see the same thing when beta counting thorium-234 and its short live decay product, protactinium-234M, another beta emitter. You might see it in any gross counting measurement where the nuclides are unknown, gross alpha, gross beta, or gross gamma. Slide 54. Pitfalls of uncertainty evaluation continued. Pitfall number 4. Some sources of uncertainty are not shown explicitly in the model. For example, variability of the instrument background or varying levels of contamination in the blank. You can either include an additional term in the model or increase the uncertainty of the blank or background count. Another example is the error due to subsampling heterogeneous solid materials such as soil or sediment. See MARLAP Chapter 19 and Appendix F for more information. Slide 55. Pitfalls of uncertainty evaluation continued. Pitfall number 5. If the model is nonlinear and some input estimates have large uncertainties, the uncertainty propagation formula may not work well. The uncertainty propagation formula is based on an approximation which may not always be adequate. To minimize the problem, keep relative uncertainties of count times, aliquot sizes, decay correction factors, detection efficiencies, and yields small. The uncertainties of the raw counts can usually be large, except for the tracer count. Slide 56. Software tools. Software tools make uncertainty evaluation and propagation easier. The Krogden spreadsheet method can be used by anyone with a spreadsheet program and knowledge of the technique. There are also standalone software programs, some of them available for free, and software component libraries that do uncertainty propagation automatically. Slide 57. GumCalc. GumCalc is a free standalone program originally developed to support MARLAP. It allows you to define a model of your measurement, specify the uncertainties of the input estimates, and propagate uncertainties automatically using the uncertainty propagation formula. It also propagates the dimensions of quantities and can perform automatic unit conversions. It can import raw data from CSV files and export results to CSV files. It's available at www.mcrone.com/gumcalc.html. Slide 58. Parting thoughts. Many people focus on uncertainty propagation as the difficult problem that prevents better uncertainty evaluations. The uncertainty propagation formula looks complicated because of the summation symbols and partial derivatives. It may be tedious to use, but it's actually straightforward. In fact, it's so straightforward that it can be implemented automatically by reusable software components. Slide 59. Parting thoughts. What's hard about uncertainty evaluation isn't propagating the uncertainty, but understanding the measurement process well enough to know what uncertainties need to be propagated. And software won't solve that problem for you anytime soon.